this is it. My favorite topic we have covered the entire year so far. We finally made it. I'm so excited. Get yourselves ready. Section 4.4, we are talking about mathematical induction. Even the term is just wonderful. Mathematical induction. So we're going to start this section by talking about what math really is in general. So I know math classes that you've taken up until now have all been about getting an answer, using a formula, using a graph. But real math, once we get through all of that, and the foundation for all of that, really lies in two things. There are two things that form mathematics. The first is conjecture, and the second is proof. So where do you think these formulas come from? Where do you think these relationships between numbers and operations come from? At some point, someone made a conjecture, someone hypothesized, they postulated that something was true. And then they proved it. They wrote a formal, rigorous proof, step by step, that logically takes you from what you know to what you want to prove, what you want to show. So there are a lot of kinds of mathematical proof. This section we will focus on one in particular, and that is mathematical induction. So let's just go through a simple example. Let's add the odd numbers. Take partial sums of odd numbers. So the first partial sum is 1. Then 1 plus 3 is 4. 1 plus 3 plus 5 is 9, and so on. You can read this box. What do you notice about the numbers on the right side here? What do you notice about them? 1, 4, 9, 16, 25. The next one is 36, then 49, then 64, then 81. These are the perfect squares. So the partial sums of the odd numbers are perfect squares. Now, someone noticed this, and it naturally led them to the next question. Is it true that for every natural number n, remember what the natural numbers are, those are the whole numbers greater than 0, the positives. Is it true that for every natural number n, the sum of the first n odd numbers is n squared? So we could check a few more numbers if we wanted. But like I said, this pattern holds. At this point, we feel pretty confident. This pattern keeps holding no matter how many numbers we check. So we want to make a conjecture. Okay? We are going to say, yes, for every natural number n, the sum of the first n odd numbers is n squared. Well, we know that the nth odd number is 2n minus 1. Okay, we remember that formula from before. Told you it would come back up. So we can write this statement, this conjecture, more precisely as the sum from k equals 1 to the nth term, wherever we want to stop, of 2k minus 1 is n squared. Okay, so I used our summation notation. So if that confused you, go ahead and think about this without our summation notation, writing out the partial sum the long way. But this is saying that starting at k equals 1 and then going up to any natural number n, the sum of those odd numbers is n squared. Okay, this is just a more formal way of writing this mathematically. At this point, this is still a conjecture. Okay, I can write a statement like that as much as I want, but it's not going to actually make it true. What I need is a proof, a mathematical proof, a clear argument that demonstrates the truth of this statement that I want to prove beyond any doubt, with absolute certainty. So like I said, there are several types of proofs in math, and one especially useful kind is called induction, mathematical induction. That's the focus of this section, as you could tell from the title. So I'm going to walk us through the basic idea of induction. And don't worry if this makes absolutely no sense to you the first time that I say this. I remember being a sophomore in Math 300, talking about the basics of mathematical proofs, and being utterly lost and confused when we talked about induction. It's okay. It takes a few times hearing this, it takes a few times trying this yourself for it to actually make sense to you. But I'm going to do my very best to explain it clearly and succinctly. Okay? So let's go through this. Let's jump right in. The basic idea of induction is this. Suppose we know some statement is true for one number. I don't care what this statement is. I'm going to call this statement P just because math, we like abbreviating things. So, for some statement P, I know it's true for some number. Let's say it's true for 1. So, using our math notation, P of 1 is true. I know that for sure. Okay? But since it's true for 1, I want to prove that P is true for all natural numbers n. Okay? I know it's true for one number, but I want to prove that it's true for any natural number that I could use. In other words, I want to show that P of n is true for any n. How do I do that? Well, if I show that P is true for some number, so say I show that P is true for any other number. Just, it doesn't have to be 1, but some random number. We'll call it K. And then I show that P is true for the number right after K. So P of K is true, implies that P of K plus 1 is true. Take a second. What if I show that if P is true for any random number that I choose, just one particular number, and I show that that proves that the next number makes the statement true. So if P of K is true, I show that P of K plus 1 is true. Then since I know that P is already true for 1, I've actually proven that P is true for every number n. Okay, let's have an analogy here. Think of this like dominoes. We started with P of 1 is true. And then I proved that if P of K is true for some K, whatever K is, it's still not certain, then P of K plus 1 is true. Well, since P of 1 is true, I can use the fact that the next number must be true to show that P of 2 is true. But if P of 2 is true, then P of 3 is true. And that means P of 4 is true. And so like dominoes, since I proved that one number being true proves the next number is true, and since I know that 1 is true for certain, every number after it has to be true. The dominoes fall, one after another, until all natural numbers n have been proven. This is mathematical induction. It will make a lot more sense once we go through an example, so let's try it. There are 2 basic steps to an induction proof. First, we want to prove that P of 1 is true. Then for the second step, the induction step we call it, assume that P of K is true. Okay? I'm not proving that P of K is true. I'm assuming that P of K is true. And I use that to prove that P of K plus 1 is true. If I do that, my dominoes fall, and I've proven it for all natural numbers n. So let's try an example. I promise it will make more sense when you see some more examples and you try some more examples. Prove that for all natural numbers n, here's my odd numbers, equals n squared. So it's the same thing as we wrote up here, just without summation notation. Same example we've been talking about. Step 1. Let's say P of n is just this statement. Okay? All I did was define this statement to be P, because I like abbreviating. Then P of 1, remember my first step is to prove that P of 1 is true. P of 1 is 1. Doesn't really equal. P of 1 means 1 equals 1 squared. Is that true? 1 equals 1. That is true. So I proved P of 1 is true. Okay? All I did was test out one of my numbers, and we saw that up here in this list. 1 equals 1. That works. Now here's the induction step, my second step. Assume P of k is true for any k, for any natural number k. Okay? If I'm assuming that P of k is true, then that means this summation up until whatever k is, the kth term, equals k squared. Notice that I'm not proving this. I'm just assuming that this is true. And the reason I can assume that this is true is because of the next step. When I use this to prove that the next number is true, it actually proves that this first one is true too. I know that's a lot to wrap our heads around, but I promise it's based in solid logic, and we can talk about this more later, truly. Okay? So don't feel bad if this is still not making sense to you at this point. Just try to stay with me for now, okay? All right, so I assumed P of k is true, then that means that this statement is true. All right. Next, we consider the next number, P of k plus 1. Okay? P of k plus 1 is going to be going to be 1 plus 3 plus all the way to the next number. Okay? P of k plus 1, still P of k plus 1. I'm still using this definition. And I want this is what I want. I want this to equal k plus 1 squared. Okay. My number is k plus 1, that's what I'm plugging in here, k plus 1 squared. How do I do this? Well, notice 1 plus 3 plus all the way to 2k minus 1. That's this. I'll even use a different color to highlight it. And we assumed that this is true, which means that just equals k squared. So k squared plus 2k plus 1 minus 1. And we want that to equal k plus 1 squared. This is still what I want. So I need to show that both sides are the same. How do I do that? I just simplify. So k squared plus 2k plus 2 minus 1 equals, multiply this out, k squared plus 2k plus 2, or not plus 2, plus 1, my apologies. K squared plus 2k plus 1 equals k squared plus 2k plus 1. And this is exactly what I wanted. I wanted both sides to be the same. So P of k plus 1 is true when P of k is true. So when this green step is true, then P of k plus 1 is true. But since, here's my conclusion, I know I kind of lost track of it here. Since P of 1 is true, and P of k implies P of k plus 1 is true for any natural number k, then P of n is true for all natural numbers n. We usually end mathematical proofs with a little box at the end to show that we've proven what we wanted to. That's it. I've proven this statement for all natural numbers n using mathematical induction. All right, I know that was a lot. Going ahead and pause, write down questions, and rewatch any section or the whole section that we just did that's confusing you. But I want to go through one more example of this because I think seeing more examples of this is more helpful than me just explaining it over and over again. Okay? So let's go through the next example. Prove that for all natural numbers n, 1 plus 2 plus 3 plus all the way to whatever the nth term is, equals n times n plus 1 over 2. Okay? In fact, this is our arithmetic partial sum formula, the one that Gauss derived, the one that we derived at the start of the year. But we want to prove that this is absolutely true for all natural numbers n. Step 1. Again, I'm going to define P of n to be one plus 2 plus all the way to n equals, so I'm just defining this as P of n so I can use abbreviations, okay? Then P of 1 is 1 equals 1 times 1 plus 1 over 2, which is 1 times 2 over 2, which is 1. 1 equals 1. So again, I've proven P of 1 is true. That's my first step in an induction proof. My second step, assume P of k is true for any natural number k. Well, if P of k is true for any natural number k, then that means 1 plus 2 plus all the way to k equals k over, or k times k plus 1 over 2. Okay, that's the induction step, the step where we assume that P of k is true. Next, we want to consider P of k plus 1, and our goal is to show that P of k plus 1 is true when P of k is true. So P of k plus 1 is going to be 1 plus 2 plus k plus 1 equals, this is what we want to show is true, equals k plus 1 times k plus 1 plus 1 all over 2. So again, I'm just using what I've defined P to be in this formula. Okay. Now again, just like before, I noticed that this first part is the same as this, which means that this is going to be k times k plus 1 over 2 plus k plus 1 equals this over here on the right. So that's k plus 1, and k plus 1 plus 1 is k plus 2 over 2. Okay. I want to show that these two things are equal. K times k plus 1 over 2 plus k plus 1. All right, I need a common denominator, so I'm going to multiply this by 2 over 2. So that's k times k plus 1 over 2 plus 2 times k plus 1 over 2 equals k plus 1 times k plus 2 over 2. Okay. Now I can combine the two fractions on the left, k times k plus 1 plus 2 times k plus 1 all over 2 equals k plus 1 times k plus 2 over 2. This is all algebra. I'm not doing anything crazy here. And now simplify, so I'm going to go ahead and multiply and distribute my numbers. So k times k plus 1, k squared plus k plus 2k plus 1 equals k squared plus 3k plus 2 over 2. And that means over here, k squared, I'll just write it out again to make it clear. K squared plus, I'm sorry, that should be a 2. The two sides are the same. So that means p of k plus 1 is true when p of k is true. Okay? And now for my conclusion, I apologize, I know it got buried again. I'm going to erase this, so go ahead and pause if you need to, but I'm going to erase everything here at the bottom. So my conclusion is, since p of 1 is true, and p of k implies p of k plus 1 is true for any natural number k, then p of n is true for all natural numbers n. Done. Whew. All right. Hope you're still with me. And again, this is not something I expect you to understand right away. If you do, that's fantastic. You should really consider majoring in math. If you don't, you should still consider majoring in math. But know that it took me a long time too to understand this. So there's only so much I can explain over a video. We will talk about this extensively in class and in tutoring and in practice. But for now, you got a taste of it. Write down major questions that you have. Try to go through my steps, go through my logic again. And don't feel bad if this is confusing to you, okay? But I promise that I will do my best to make sure this is not confusing to you in the end. All right. Thank you so much for staying until the end. Have a great rest of your day.